Hi, in this Math from the Gut video, we'll prove the Pythagorean theorem in a very intuitive way. After some effort, you should be able to mentally prove this very important equation in less than 2 blinks of an eye forever. Along the way, you'll also learn a powerful tool that should prove quite useful later on in physics and math. Beware that this video is a bit advanced. You should already be quite comfortable with using the Pythagorean theorem and with the basic terms surrounding it. Also, some familiarity with vectors and basic algebra, while not assumed, will be helpful. So, let's get started with a general right triangle having legs of lengths A, B, and C. Now, let's rotate it so that its legs are horizontal and vertical, like this. We can do this rotation with any triangle, and it makes things easier to talk about. Now that it's rotated, we can give the legs the more obvious names of X for x-axis, Y for y-axis, and H for hypotenuse, and call their lengths lowercase x, y, and h respectively. More specifically, we'll refer to this triangle as having an x vector, a y vector, and an h vector. Don't worry if you've never used vectors before. Just think of a vector as a line segment that is defined by how much it goes across and how much it goes up down. We'll touch on this a bit more later. And finally, because I find it much easier to work with numbers instead of letters, I'm going to assign actual numbers and use a 5, 12, 13 right triangle in my proof. Say what? Can you do that? Oh, I can hear the howls already. You can't prove things with numbers. That's not fair. You're cheating. You're trying to prove something and you're already assuming the answer of 13. Well, that's actually not true. If you're not convinced, just do this. Every time you hear me say 12, just think X. When I say 5, think Y. And of course for 13, think H. For example, if I say 12 over 13, just think x over h. Do this and you'll have your general proof with x, y, and h where absolutely nothing is assumed. I hope you'll agree that this is a really nice way to think about things. We simply work with known lengths that are easier to relate to. The general proof then immediately falls out from what we're doing. So, let's think of the h vector as being made up of 2 perpendicular vectors, an x vector and a y vector. Now watch the red dot and see how moving along both component vectors x and y gets us to the same place as simply moving along the hypotenuse. Here it is again. And here is the equation for that. Notice that the little arrow decorations here on the top of h, x, and y indicate that these are vectors instead of just simple numbers. Our h vector, for example, can be represented by 12, 5. Since it goes right 12, let's call them inches, and up 5 inches. Starting with our original equation, let's try out a little vector arithmetic. So we've seen how to represent the h vector. How then would we represent the x vector? Well, it goes right 12 inches and doesn't go up and down at all. In other words, it goes up 0 inches. Hence, it is represented as 12, 0. Likewise, the y vector only goes up 5 inches and is therefore represented as 0, 5. Think about this a bit if you need to. When we add vectors together, we add their x and y lengths separately, like this, to get their combined x and y distances. So, we see that x plus y really does equal h. This makes sense since moving along the h vector moves us 12 inches right and 5 inches up. And moving along both component vectors does exactly the same thing. It just does one of the movements at a time. Okay, so let's return to our numbers and consider just these 2 remaining vectors for now. Question: As we move along the hypotenuse, how much progress are we making in the direction of the x vector at the same time? In other words, how much of our movement along the 13-inch vector is in the horizontal or x direction? You might want to pause and ponder here. Hopefully, you can see that moving along the hypotenuse also moves us 12 inches to the right in the x direction. Now, moving along h also moves us 5 inches up, but those 5 inches don't move us at all in the x direction, since it's perpendicular. A fancy way to talk about the movement of h in the x direction is that the h vector's projection along the x vector is 12 inches. This should all make sense since some of our movement when we move along h is also in the y direction. It's not all focused in the x direction. Because of this extra effort, we need to move more than 12 inches along h to achieve a final horizontal movement of 12 inches. By watching these two red dots, we can see how actual movement along h also moves us along in the x direction at the same time. Here it is again. Let's now keep these vectors locked together, but move them around and rotate them some random amount, like this. Does this change how much the h vector projects onto the x vector? Of course not. It's just like we drew this whole thing on a piece of paper and then moved the piece of paper around on a table. The drawing is still the same. The relationship between these two vectors is still exactly the same. Obviously, none of our distances or projected distances has changed. The hypotenuse still breaks down into two perpendicular vectors of lengths 12 and 5. Hopefully, this sets us up nicely for my next question, where we move along the x vector instead of the h vector. So, here we have the h vector. Now, if we move 12 inches in the x direction, like this, then some of that motion will be in the h direction. But we're doing math here, and we want to know exactly how much of that motion moves us in the h direction. Please pause and ponder a bit. Okay. Although it's tempting, I hope you didn't fall into the trap and say that we project 13 inches along h just because the h vector is 13 inches long. It doesn't work that way. Just because the h vector happens to be 13 inches long doesn't mean that we project along its entire length. Think about it. The most efficient way to go along h is to go straight in that direction. If we want to go 13 inches along h, the shortest way to do it is to go 13 inches directly along h. Hopefully pretty obvious, right? Certainly, going less distance, say 12 inches in some other direction like x, isn't going to move us the full 13 inches in the h direction. I can't walk 12 inches in the x direction and expect that just a part of that motion will move me 13 inches along h. Any ideas yet what the answer is? Think about symmetry. Think about how each of these vectors should be related to the other vector in the same way. Remember how h projected onto x before? Please, replay the video if needed. Okay, let's add labels to keep things clearer. And then change how we look at things by rotating the two vectors together, like this. Keep this in mind. We started like this and rotated to this. We've now lined up the hypotenuse with the x-axis. Hopefully you can see more easily that when we move 12 inches diagonally along the x vector, that we move less than 12 inches along the hypotenuse, or with this new orientation, the x-axis. So, how much does it move us horizontally when we move along this new rotated x? Does this help? Think back to how much the h length moved us along the x length. Think about how similar this is. Please, pause, and ponder. It's much better if you get some of this for yourself. Returning to our original triangle, remember that we moved 12 inches along the x-vector's direction as a result of 13 inches moved along h. So there was a ratio of 12 to 13 there. 12 inches projected on x for every 13 inches moved along h. So, for every 12 13ths projected along x, we had to move 13 13ths or 1 inch along h. In other words, each inch moved along h causes us to move 12 13ths of an inch along x as a side effect. If we repeat this 2 more times, we continue with this proportion and see that 3 inches moved along h moves us 36 13ths of an inch along x. Now, let's go back to our picture where h is rotated into the horizontal direction instead. Notice that the angle between our vectors doesn't change when h and x are rotated together. Remember, it's just like they are both drawn on a piece of paper and we rotate the paper. So we still have the same angle here, which happens to be about 22 degrees. Now, if we move 1 inch along the x-vector, how far would we move in the direction of the h-vector? We're just asking how much we end up moving in that direction. We still have exactly the same angle between the vector that we move along and the vector that we measure the projection along. Please pause here if needed. Hopefully, you are starting to see that each inch that we move along the x-vector also moves us 12 13ths of an inch in the h direction as part of its motion. Like this. Look familiar? It's exactly like when we moved along h before. The original picture where we move along h is just the mirror image of this picture where we move along x instead. Moving 1 inch along either vector moves us 12 13ths of an inch in the direction of the other vector at the same time. So, for the big question, if we move the full 12 inches along the x length, how many inches have we moved in the h direction at the same time? We've already discussed what happens if we move 1 inch or 3 inches in the x direction. We just have to extend the pattern a bit. Pause if needed. Okay, every inch that is moved along the x length means 12 13ths of an inch that is moved in the h direction. So, 12 inches in the x length means that we move 12 inches times 12 13ths, or 144 13ths of an inch in the h direction. So, this gives us the contribution of the x vector to the total length of h, the hypotenuse. Can you see where I'm going with all of this yet? To help, let's look at the big picture to remember what this 144 13ths of an inch represents. Pause and ponder to see if you can figure out what's coming next after we do this. So, remember that this distance is 12 times 12 13ths, the projection of our x vector in the h vector's direction. Again, it's how much our x vector contributes to h's total distance. So what does this remaining distance represent? It's the projection of the y vector in the h vector's direction. Moving along the x vector gets us part of the way along h, and moving along the y vector gets us the rest of the way. Can you figure out what the second distance actually is? If we also know this distance, then h is just the sum of these two distances. Okay, so to determine the second distance, let's go back to our triangle and focus on the y vector and the h vector this time instead. Watch the red dots. When we move 13 inches along the h vector, how much do we also end up moving in the downward direction of the y vector? Hopefully, you see that we move 5 inches along the y vector, since the 13-inch hypotenuse moves us down that much. So, moving 13 units along h causes us to move 5 units along the direction of y as a side effect. Now, what ratio applies if we move along the y vector instead and we want to know its projection on the h vector? It's exactly the same idea as when we were working with the x vector before. When we worked with x and h before, we saw that the same ratio applied regardless of which vector we moved along and which one we projected onto. So, we should expect that this 5/13 ratio also applies when we move along the y vector directly instead of h. We expect that moving 13 units along either the h or the y vector will move us 5 units in the direction of the other vector at the same time. To see this more clearly, we spin things like this to orient the h vector horizontally again. And here's the picture. Hopefully, you see from all of this that each inch we move along y moves us 5/13 of an inch along h as a side effect. It should at least be clear that our movement along y is much larger than our projected movement along h. You may have noticed that the ball moving along y was going much more quickly than the one across h. Here are the dots again. Mathematically, the total movement along h is the 5 inches along y, times our y to h movement ratio of 5/13 for projected distance along h of 25/13. So, let's step back and look at what we're doing by looking at the entire rotated triangle. We first move 12 inches along the x vector, which moves us the shorter distance of 12 times 12/13 of an inch along h. Moving along this rotated x vector also moves us down by this distance, but we're not concerned about that distance here. No one's asking for it. We're only concerned about the projected distances along h. Then we move 5 inches along the y vector, which moves us the remaining 5 times 5/13 of an inch along h, and back up by the same distance. Notice how the up and down distances here cancel out. First we go down, then we go right back up. That's why we don't care about these distances. They can be thought of as the wasted effort that doesn't move us along the hypotenuse when we move along the legs. At the end of the day, we're just left with the total motion across h. Observe how all of this still holds true no matter how we rotate the triangle. So we can do this and get back the triangle with its original orientation where x is horizontal and y is vertical. Everything I just said is still true. This relationship between all of these vectors is still exactly the same. It's just a bit less obvious when seen this way. Now, let's write down what we've done. If our projected distance calculations are correct, and if 13 is really the correct hypotenuse length here, then our total hypotenuse length of 13 should equal 12 times 12/13 plus 5 times 5/13, or 144/13 plus 25/13, which is 169/13, which exactly equals 13. So, it looks like things are working out. Now, for the teensy bit of algebra. Even if you haven't learned algebra, see if you can follow along. Let's return to our original equation. Keep in mind that both sides of this equation are equal. We just showed that. So, if we multiply each of these sides by our circled 13s like this, things will still be equal. It's just like making both ends of a balanced seesaw 13 times heavier. The seesaw would still be balanced, but everything would just be 13 times heavier. Distributing the red circled 13 to the first term, the multiplication and division by 13 cancel out, and we're left with 12 times 12. Similarly, distributing the same circled 13 to the second and final term, we get 5 times 5. Think about what I did here a bit if you need to. Of course, this new equation can now be written more compactly as 13 squared equals 12 squared plus 5 squared. You may have noticed that the Pythagorean theorem is now staring us in the face, but of course we're using specific numbers instead of general letters or variables. Remember, though, that we can substitute these numbers with their corresponding variable names at any time. Doing that gives us this. Or even this. We're now clearly looking at the Pythagorean theorem. But you promised me 2 winks, and you've been talking for so long. I can't keep my eyes open forever. Well, I did that to help you understand everything. If you've been properly prepared, you'll now be ready to see everything in 2 winks. Let's bring up our rotated triangle again. Now, I'm going to change things slightly to make the proof even faster. Rather than starting with h equals, let's say h times the projection of h onto h equals. Projection of h onto h. What does that mean? Well, if we move 13 inches along h, then we also project the same 13 inches on h. They're the same vector. Hopefully that's pretty obvious. And a ratio of 13 to 13 is just 13/13 or 1. Similarly, we can also say that if we move h inches along h, then we also project h inches along h. For h, the ideas of movement along and projection onto are the same thing. Now, for the 2-blink demo. Ready? H times its projection onto itself equals x times its projection on h plus y times its projection on h. 1 blink. Hopefully, you can see all of that faster than I can say it and show it. With a little practice, you should be able to. Finally, multiply by h on both sides to remove the common denominator. Here it is again, in case you missed that. And we're done. Second quick blink. Go over this a few times until you can see it quickly and start to feel it in your gut. Now, for the grand finale. Let's see if we can do this whole thing in 1 blink. Try following along. First, note that the ratio for h's projection onto itself is h over h, which is proportional to h. Likewise, the ratio for x's projection on h is x over h, which is proportional to x, and y's projection ratio on h is y over h, which is proportional to y. So, using these simple proportional projection ratios instead, we can say that h times its projection equals x times its projection plus y times its projection. Done. 1 blink. All we're really doing is moving from one side of the h vector to the other in 2 different ways and computing the distance. The distance along h using the direct way, where we move along h, is proportional to h squared. The projected distance along h when we move along the x and y legs instead is proportional to x squared plus y squared. So, we're done with the proof. Now, if you'll indulge me, I'd like to drive one final point home. Let's return to our 5, 12, 13 triangle. The question is how many times greater the 12-inch leg's contribution is to the hypotenuse length than the 5-inch legs. Please pause and ponder and see if you can figure this out from what we've already done. One obvious answer would be to say that 12 inches is 2.4 times longer than 5 inches, and that its contribution to h is therefore 2.4 times longer. But that answer fails to also consider the fraction of each leg's length that contributes to the hypotenuse. Remember that the 12-inch leg not only goes a distance that is 2.4 times longer, but each inch of that distance also moves us 2.4 times farther along the hypotenuse than does each inch of the 5-inch leg. This is clearly because the 12-inch leg lines up more closely with the hypotenuse than the 5-inch leg. The 12-inch leg is headed 2.4 times more in the direction of the hypotenuse than the 5-inch leg. So, overall, the 12-inch leg's contribution to h isn't just 2.4, but is rather 2.4 times 2.4, or 5.76 times greater. That's quite a bit more than just 2.4 times bigger. The first factor, 2.4, is for the length ratio, and the second is for the ratio of the projections onto the hypotenuse per unit length. More formally, but a bit less intuitively, we can determine this ratio by taking the ratio of the projected distances from the pieces of this equation that we used before. Dividing the x vector's projection on h by y's projection on h, we get this. Since the division by 13 is in both the numerator and the denominator, it cancels out and we get our expected ratio. Thanks for hanging in there. I hope you were able to follow all of this. I hope that the ideas were so compelling that you'll still be able to piece this proof back together 2 weeks or even 2 years from now without peeking, but maybe with a little blinking.